Photoelectron spectroscopy allows for an analysis of a sample and for the determination of the binding energies of the electrons within that sample. How much energy is required to remove the electrons? This allows one to know what element one has, but also just deeper information about what the atom is and about orbitals and the energies of electrons around the nucleus. So it works by shooting light of certain energy from generally an X-ray, and that energy that hits the sample and ejects an electron from that sample. The electron can then be detected, and its kinetic energy can be measured. And additionally, the relative numbers of electrons and their kinetic energies can be found. Now, the kinetic energy is very important because knowing the kinetic energy of the electron ejected and the original energy of the photon absorbed by the sample, one can know the binding energy of the electron. You see, a certain amount of energy is added as the photon, okay, and then to eject the electron requires a certain amount of energy, the binding energy, the energy to take the electron from the core level to the vacuum level, as if it's just floating in a vacuum away from all positive charge. And then oftentimes the electron will have some additional kinetic energy beyond just being ejected from the atom. It is moving with differing amounts of speed and therefore having differing kinetic energies. Yes, we can see that this overall energy of the photon should be equal to the binding energy plus the kinetic energy of the emitted electron. And realizing that the difference between the energy of the photon and the kinetic energy of the electron is the binding energy, we can calculate for binding energy. Yes, the binding energy of the electron is the energy of the original photon minus the kinetic energy of the electron ejected. So we can learn the binding energies of these electrons on a variety of different elements. First, let's take a look at two elements, hydrogen and helium. We can see a graph of the relative numbers of electrons versus their binding energies for these two elements. Now, hydrogen, it has a binding energy which is moderately high, and helium, you can see, has a higher binding energy, the energy to emit each electron on its 1s subshell. You see, these two different elements have different binding energies because they have different numbers of protons. Coulomb's law says that the energy of a charged system, potential energy of it, is equal to a constant times the charge of one object times the charge of the oppositely charged object divided by the distance between them. And so we can see that the helium atom, which has two protons, it has twice as much of some positive charge, Q2, compared to hydrogen. And so having twice as much protons within it, there should be quite a bit more attraction between electrons and the nucleus, and therefore more energy is required to eject those electrons. The helium has a higher binding energy. So you can see that hydrogen, its binding energy is about here, but helium, it's a little bit to the right. Now, going further, we might also note that there is a larger curve under the binding energy for helium's 1s subshell than for hydrogen's, because there are twice as many electrons that can be emitted from helium as hydrogen. So going further, we can take a look at lithium. This has 2 electrons in the 1s subshell and 1 electron in the 1s subshell, 2s subshell. These have differing binding energies because there is a differing amount of attraction between the electrons and the nucleus. You see, the electrons in the 1s subshell, they are quite close to the nucleus, and therefore they have high binding energies. It's difficult to remove those electrons. But the electron in the 2s subshell, this has a much lower binding energy because it is further from the nucleus, but also it's shielded from the nucleus somewhat by these electrons in the 1s subshell. So there's a great attraction to the nucleus, but there's significant repulsion from those inner or core electrons in the 1s subshell. And so the electron in the 2s subshell is much further to the left. It's got a much lower binding energy. Now, please note that for lithium, the curve with the higher binding energy, the 1s electrons, it's higher and has greater area than the curve for the electrons from the 2s subshell. This is because there are twice as many electrons in the 1s subshell as in the 2s subshell. So the area under the curve for the 1s should be twice the area under the curve for the 2s subshell. So considering that, you can take a look. At this spectroscopy and decide what element this is. So you might see that it has greater binding energies for both of its curves compared to lithium, and that the areas under the curves for both of these peaks, they are equal to each other, suggesting that you know that there must be 2 electrons in the 1s subshell, therefore might be, same number, 2 electrons in the 2s subshell. You might surmise that being that there are as many electrons in the 2s as the 1s subshell, and that there's a greater binding energy for these electrons than for lithium, therefore there might be more protons, you might figure then that you are dealing with beryllium. And so you see how you can analyze for what elements you're dealing with by this spectroscopy data. And one final example, you have yet greater binding energies than in the case for beryllium, yet there's also an additional peak, which has lower binding energy than the 2s subshell. It's suggesting that there's additional electrons in the 2p subshell. Yes, you have a 2 to 2 to 1 ratio for the areas of these peaks, suggesting that there might be 2 electrons in the 1s, 2 electrons in the 2s, and 1 electron in the 2p. Later, when you get to organic chemistry, you'll find that nuclear magnetic resonance studies, NMR, are very much like these, and also provide information about what substance you're dealing with. Thanks for watching, guys.